Hello, my name is Roy Ramirez from AREX, and in this video I would like to go over the results of the first hot fires of the P-5 liquid rocket engine, the first liquid rocket engine from the Central American and the Caribbean region, built in Costa Rica. I try to make this video very detailed and explicative, in a way that anybody could learn about propulsion as they watch it and actually understand the results of the P-5 engine. Therefore, this is a long video, and if you do not have experience with propulsion, I would highly recommend watching it completely. Here's an index of the topics I will cover, so you can skip any sections as you wish. Let's learn about how rocket engines work and how they are started. You may want to skip this part if you are already familiar with rocket engines. This image represents a model called the fire triangle, which states the ingredients required to start a fire. The first ingredient is the fuel. Some examples of fuels are wood, gasoline, methane, hydrogen, and many other hydrocarbons. The second ingredient is the oxidizer, which most of times is the oxygen readily available in the atmosphere. Nevertheless, in the case of spacecrafts which travel to space where there is no oxygen available, it is necessary to carry an oxidizing agent, like oxygen for example. Some examples of oxidizers are liquid oxygen, nitric acid, hydrogen peroxide, and potassium nitrate. In rocketry, the fuel and the oxidizer are known as the propellant, and their specific choice determines the type of rocket and generally its application. For chemical propellants, there are three main types of rocket engines: solids, liquids, and hybrids. In solid rockets, the propellants are in a solid state, usually as powder, and are mixed or blended together at a specific mixing ratio. This mixture, which is called the propellant grain, is encased in a combustion chamber and sometimes a nozzle is added. Once the grain is ignited, the combustion reaction cannot be stopped, and so most of the time no components like tanks, pumps, or valves are involved, which makes the designing, building, and testing process less complex. Solid rocket motors are commercially available to hobbyists, like the one in the left, and they can be even built with household materials. Usually, to increase the power of a rocket motor, it is required to make the propellant grain bigger, which is a limitation. On the other hand, liquid rocket engines store liquid propellants in tanks and use a complex feed system to deliver the propellants into the combustion chamber through an injector. Generally, pumps, tanks, valves, pressure regulators, cooling systems, preburners, and many other components are used. This kind of engines can usually be shut down, throttled, and sometimes even restarted. Finally, hybrid engines are somewhere in between liquid and solids, generally using one solid propellant and the other either gaseous or liquid. The third ingredient in making a fire is a source of heat like a match or a spark. In the case of rocket engines, there are several ignition methods which work for different propellant choices. There are pyrotechnic igniters, spark plugs, using a smaller solid propellant grain, or perhaps you have even heard about the Russians lighting up their engines with oversized wooden matches. Even more exotic, there is also hypergolic ignition, a method in which two propellants called hypergolics combust spontaneously at contact without any external source of heat requirement. So to summarize, when fuel, oxidizer, and a source of heat are combined in the right mixture, combustion occurs. Keep in mind the words right mixture, because as you may have noticed, when you add too much oxygen to a fire by blowing on it, you can end up extinguishing it. Now when we talk about a hot fire, we mean a type of test in which propellants, that is the fuel and the oxidizer, flow into the engine and are ignited by an external source. The idea is to achieve the design conditions of the system, which in this case are the flow rates and mixing ratio of the propellants, and then compare the experimental results to the theory. Now that we're done with theory, we're going to talk about the different ignition methods used for the P-5, which again is a liquid rocket engine, and the full engine hot fire attempts. What I mean by full engine is that the combustion chamber was used, since before these tests the injector was hot fired successfully without the combustion chamber. If you want to learn more about it, click here or in the link below. First, here's a quick overview of the hot fire dates and the results. I will explain the ignition methods afterwards. On August 3, 2019, there was a first round of hot fire attempts. An aluminum prototype was used, and the engine was meant to operate for only 3 seconds at 50% of its full capacity. The methods used were internal solid propellant load (ISPL) and external flame. There were about 5 attempts without success. On August 14th, history was made. The final version of the engine was tested 7 times, with the 2 final attempts being successful. The methods used were ISPL again and internal fuel-soaked load. Nevertheless, it was not able to operate the engine at 100% of its capacity. On August 16th, a final attempt to operate the engine at full capacity was made. The same 2 methods from the last testing day were used for a total of 16 attempts and 6 successful ignitions. If you want to skip any of the hot fire dates, the timestamps are in the description below. Now we will explore what the ignition methods are and then get into the actual footage and results of the 3 hot fire dates. The first ignition method, which is the internal solid propellant load or ISPL method, consisted in lighting up a small rocket propellant grain placed inside the combustion chamber. Since the grain has its own oxidizer, it can burn inside the combustion chamber without requiring any oxygen from the surrounding air. The grain was wrapped in a piece of cloth and then carefully inserted up the throat in a way that it wouldn't fall off the engine. Once the cloth is lit up with a lighter or match, the fire spreads until it reaches and lights up the grain. The grain, which is made of a simple sugar-potassium nitrate mixture known as rocket candy, starts burning at a known time rate, and then the computer proceeds to inject the propellants. In this method, it was assumed that the byproducts of the grain's combustion would not affect significantly the combustion of the liquid propellant. Moreover, almost immediately after the engine lights up, the pressure in the combustion engine must build up quickly enough to eject the cloth and any propellant residue. The second ignition method uses an external flame for a burner such as a blowtorch. The flame is aimed diagonally into the chamber and fixed with supports. Once the flame is going, the engine is fired. The third method uses an internal fuel-soaked load. Like ISPL, a cloth soaked in fuel is inserted into the combustion chamber and then lit up. Once it starts burning, only the bottom part of it will burn, since there is no much oxygen available inside the chamber. After ignition, the pressure in the combustion chamber must build up quickly enough to eject the cloth. Before we get to the hot fires, there are some limitations viewers should be aware of. AREX is by no means a high-power propulsion organization. AREX is an amateur experimental propulsion startup that focuses on exploring aerospace technologies with the purpose of contributing to the globalization of space. That is, making rocket science more accessible by trying to not make it rocket science. This being said, all sophisticated components like turbopumps, cryogenics, venturis, hypergolic igniters, regenerative cooling, hydraulic actuators, etc. were beyond the scope of the P-5 engine, since it was necessary to keep it simple to understand better what building an engine meant from a technical, manufacturing, and economical point of view. Another limitation was the time allotted for building and testing the engine. The total time spent over the summer building and testing the engine was about 1,200 and 1,300 hours in a period of 3 months, the last day of work in the schedule being August the 16th. After that day, it was not possible to continue working. Moreover, all hot fires happened during nighttime, since it would usually take an entire day to prepare and set the testing zone. Some tests were recorded with a phone camera placed at a safe distance lateral to the engine. When the flame of the engine comes out, there is a high contrast between the surrounding darkness and the flame, which makes appreciating the scene somewhat difficult. Also, for the last hot fires, we managed to get a higher quality GoPro camera, but unfortunately it ran out of battery before any test worked. Therefore, we apologize for the quality of the footage, and we will use this experience to better plan the photographic side of our future projects. Lastly, it was decided to mount the engine vertically and use a slab to deflect the flame. Nevertheless, the angle to which the slab was set was not high enough, and so part of the flame rises, making it more difficult to observe. Again, we apologize, and we plan to orient our future engines horizontally. Now we will proceed to the actual hot fire results, beginning with the first series of attempts, which happened on August 3rd, 2019. As already mentioned, the idea was to test a prototype of the engine in aluminum at about 50% of the actual power. These tests were originally scheduled to happen a week earlier than expected, and to be done in one specific location in the province of Heredia, where the atmospheric conditions were measured. Nevertheless, due to timing, it was decided to operate the engine in San Rafael of the province of San Jose just 5 minutes away from the Cartago province. The test bench was placed at a safe distance from the control room inside the Alberio Amateur Propulsion Laboratory. All the working personnel was prepared with safety equipment including chemical gloves, fire extinguishers, goggles, and a water hose. Since it had been often raining in the last weeks of July, a tent was used. It usually took from 9 a.m. in the morning to about 6 p.m. to follow a strict list of preparations before the engine was ready to fire. During this time, the engine was cold-flowed to reaffirm the validity of the experimental models derived, the propellant tanks were filled, and the safety equipment was installed. Keep in mind that refilling the tanks would usually take about 40 minutes, and the time it takes to remove the combustion chamber from the injector so that the injector can be cold-flowed is close to 1 hour due to the complex assembly between them and the plate that holds them to the bench. Without further ado, here's how not to light up a rocket engine. We begin with the external flame method where a blowtorch is used. Let's watch. As we can see, once the propellants come out, they extinguish the flame. In the second method, which is ISPL, a grain of rocket candy was inserted and then lit up.
Yeah.
It might be difficult to see due to the smoke, but if you look carefully, you can spot the propellants coming out without burning, just like in the past test. In this attempt, a wooden stick was used instead of the suggested cloth, and the propellant grain was probably too big. Nevertheless, this was not the real cause it didn't work out. As we're going to see in other videos, even with a small propellant grain in a cloth, this method does not work at all. We'll explain why by the end of this video. You may have also spotted the small low-profile camera in the bench. This is the closest we have ever recorded the engine while firing until the camera melted. Lessons learned. Nevertheless, in this video we can still appreciate how the propellants don't even combust. The yellow powder visible in some of the videos are residues of the fire extinguisher. The second series of attempts happened during August the 14th. And we used the final version of the rocket engine, which was made from stainless steel. In this video, the ISPL method was used.
4, 3, 2, 1.
We can see how the propellant grain burns, and in the last 3 seconds, a stream of propellants comes out of the engine without combusting. Metallic cables were used to hold the cloth and propellant grain in place. This method was tried 3 times and then it was switched to internal fuel-soaked load, which consists in inserting a small cloth soaked in fuel inside the combustion chamber. Now let's watch the first successful hot fire and comment a little bit. After reviewing all the hot fires, we will analyze these in detail, including data. First, we can see that the cloth burns well on the outside, and even though the video was cropped, most of the time we let the cloth burn for about 45 seconds so that it would warm up the engine and let the fire grow. Another interesting thing to notice is that after the test, we can still see fire in the deflection plate and the exit of the engine due to the presence of excess fuel that did not burn with the oxidizer. It is easy to tell when this happens since the flame color of the fuel burning with the air has that characteristic blue at the bottom, while for the oxidizer, the color is more like an orange with a tinge of magenta. Let's go quickly over some frames of the video. In the first one, we can see the cloth burning at the exit of the engine. In frame 2, the engine injects the propellants, they ignite at a predicted mixing ratio, and enough chamber pressure builds up to eject the piece of cloth. In frame 3, the cloth reaches the ground and burns violently due to residual fuel in the deflection plate. In frames 4 and 5, we can actually see how the exhaust plume develops and notice the presence of oxidizer in the flame, which is indicated by the orange-magenta tinged color. The original idea of the deflection plate, as already mentioned, was to deflect the plume. Nevertheless, the plate was fixed at a very small angle, and instead made more difficult to appreciate the hot fire. Finally, in frame 6, we visually reaffirm the abundance of fuel as evidenced by the blue fire in the bottom of the flames. In the data files produced by the computer, we got readings of both thrust and chamber pressure, which confirms the existence of a combustion reaction inside the engine due to the ignition of a mixture of liquid propellants. So now the question, would this be considered a liquid propellant rocket engine, arises. Let's take a look at the conditions required for an engine like this. According to Sutton and Biblarz, a liquid propellant rocket propulsion system consists of one or more thrust chambers, one or more tanks to store the propellants, a fit mechanism to force the propellants from the tanks into the thrust chamber, a power source to furnish the energy for the fit system, suitable plumbing or piping to transfer the liquids, a structure to transmit the thrust force, a control device to initiate and regulate the propellant flow, and thus the thrust. Moreover, the same author defines a thrust chamber as a device where the liquid propellants are metered, injected, atomized, mixed, and burned to form hot gaseous reaction products, which in turn are accelerated and ejected at a high velocity to impart a thrust force. A thrust chamber has three major parts: an injector, a combustion chamber, and a nozzle. Since the P-5 met all these requirements, it is appropriate to classify it as a liquid propellant rocket engine, thus making history that day at a regional level. Nevertheless, remember we mentioned to keep in mind the mixing ratio? Okay, keep the thought as we go through the remaining videos so that you can understand better the analysis we're going to do later. Now we're going to see more videos of other tests that occurred that day. All of them again use the IFSL method, which was the only one that worked. In these hot fires, the mixing ratio, which again is the amount of oxidizer relative to the amount of fuel, was varied. Some videos are repeated but from a different angle. Let's watch.
Fire.
Which of those two hot fires would you say had a higher mixing ratio? One side note, the propellant mixing ratio is commonly written as either R or O/F. If you would like to guess this answer a little bit more informed, again you can watch the injector hot fire videos by clicking here or in the link below. Anyway, don't worry since we'll show some of those videos by the end. The final and third hot fire date occurred during August the 16th, and this was the day we got a more professional camera which unluckily died before we got ignition. We will begin with the unsuccessful attempts for which the much better camera was still alive and recording in slow motion. In this attempt, the ISPL method was revisited. Let's watch. It is very interesting to see how pieces of the propellant grain start to come out of the engine as it burns, and eventually what was left of it comes out spinning and explodes against the deflection plate. About 1 second later, we can see how the propellants just come out at the wrong moment. This all happened very fast, but the video is in slow motion. Now you could have probably thought, what would have happened if the timing would have been right? Well, let's watch the next video. If you look carefully enough, you can see that the outer tip of the propellant crane is burning and shooting a jet of combustion gases. But once the propellants are released, they are not ignited and eject the propellant load instead. Afterwards, the internal fuel-soaked load method, which we know to work, was revisited, but to our surprise, it failed. Let's watch. As we can see, once the propellants are injected, they eject the cloth and the mixture does not combust. But why? Well, let's try one more time with the same ignition method. In these hot fires, the ignition was successful, but a much more lower mixing ratio was used. This means that the mixture was fuel-rich. It looks like we could make our first conclusion, which is, the only working ignition method is the internal fuel-soaked load method, but it only works for a specific range of mixing ratios. Based on the hot fire we just saw, we get the following three questions. What is the ignitable mixing ratio range? Why any mixing ratio outside the range will not ignite? And how does this affect the engine? Next, we will proceed to the analysis and explore the answers to these three questions. There will be some math involved, but don't worry. What is important is that you understand what the equations tell us about what's going on at a physical level, not the math itself. The first question, which is, what was the ignitable mixing ratio range, can be simply found by looking at the data of the successful hot fires. To better understand the concept of mixing ratio from a physical point of view, I'm going to introduce some equations and a little bit more of theory. The first quantity we need to learn about is called the mass flow rate, which is denoted by an m with a dot on top of it. The square brackets in the equation 1 indicate the dimension of the quantity, which is precisely mass over time. This means that, for example, its units could be kilograms per second, grams per hour, or even pound mass per minute. A stricter definition of the mass flow rate would be the derivative of the mass inside a controlled volume with respect to time. But for simplicity's sake, we can just think of it as the number of kilograms of propellant that come out of the engine per second. The second equation is pretty simple. It states that the total mass flow rate in the engine equals the mass flow rate of the oxidizer plus the mass flow rate of the fuel. When we know the mass flow rate of the individual propellants, we can calculate the mixing ratio, that's OF or R, by simply dividing the oxidizer mass flow rate by the fuel mass flow rate as given by equation 3. Sometimes it comes in handier to talk about volumetric flow rates, denoted by a capital Q, instead of mass flow rates. Equation 4 shows that if we know the mass flow rate of a propellant, we can simply divide it by its density, denoted by the Greek letter rho, which looks like a P, and get the volumetric flow rate, which is sometimes simply called the flow rate. Its dimension is length cubed divided by time, so some common units are liters per minute, meters cubed per second, or in our case gallons per minute, abbreviated GPM. Therefore, it is also possible to express the mixing ratio as a function of the volumetric flow rates and densities of the propellants as given by equation 5. If we assume that the changes in density are very small, relative to the propellant's densities at standard temperature pressure conditions, we can think of the term rho sub O divided by rho sub F as constant, and thus we can conclude that the mixing ratio is directly proportional to the flow rate of oxidizer and inversely proportional to the flow rate of fuel. This means that if we flow more oxidizer, we're going to get a higher mixing ratio, whereas if we flow more fuel, we're reducing it. How can we control the flow rates of the propellants? Well, in our case, we do this by setting the pressure in each of the propellant's tank to a desired pressure. To correlate the tank pressure with the resulting flow rates, more than 120 cold flow tests were done. By analyzing the results from these tests, an experimental model like the one in the bottom can be obtained and used to determine the required tank pressures to achieve a desired flow rate. If you want to learn more about these cold flow tests, you can click here or in the link below. Let's do an example. Here we're going to try to use the model to predict the required tank pressures to achieve a mixing ratio of, let's say, 4. We have three main equations. The first two are exponential equations which come from the model where P stands for tank pressure, and the third one, which is the definition of the mixing ratio. If we plug the first two equations into the third one, we're going to realize that there is only one equation and two unknowns, that is, the tank pressures. This means that we have infinitely many solutions where one pressure can be found as a function of the other and a desired mixing ratio. Solving the system of equations, we get equation number 4. Don't worry if you're having trouble understanding the math. The important thing to notice is that the resulting equation is telling us that there is more than one combination of tank pressures that achieve that mixing ratio we want. In our problem, R equals 4, and let's pick a tank fuel pressure of 100 pounds per square inch, or PSI for short. Solving equation 4 with these inputs, we realize we would require an oxidizer tank pressure of about 165 psi. But for example, I could still achieve an OF of 4 with another oxidizer to fuel combination of tank pressures, such as 91 to 50 or 302 to 200. So which combination should we pick? We will talk about that when we answer the third question. It is also important to keep in mind that there is a limit to the pressure the system can handle. This limit is called the maximum allowable operating pressure, and it was set to 200 psig, including a safety factor. This means that any pressure tank combination that exceeds this number is not allowed. Why would we prefer a mixing ratio over another? Well, if you remember when we talked about the fire triangle, we mentioned that in order to have combustion, the three ingredients must be present at the right proportions. This means that there will be simply some cases where there is so much fuel present that the mixture won't light up at all, or vice versa. It is even possible to have just the right mixing ratio but not enough heat to start the reaction. But let's say you have two mixing ratios and you know you can light up the engine for both of them. How do you know which one is preferable? Well, in very simple words, the one that produces the highest exit velocity of the combustion gases is the best. When we divide this exit velocity by the acceleration of gravity, we get a quantity that is very important in rocketry called the specific impulse, or ISP for short. This is the quantity we want to maximize, and it is in units of seconds. The higher the ISP, the better. Predicting the ISP based on the mixing ratio is a very complicated task, since it involves a lot of rocket theory involving complex thermochemistry. Therefore, engineers usually use a software like NASA's Chemical Equilibrium with Applications, or CEA, to predict this. In the case of the P-5, AREX developed a software 3 years ago called the Rocket Engine Designer, or the RED, that links with NASA's CEA to get initial data and then solve many parts of the design of a liquid rocket engine. The RED can quickly analyze the relationship between the ISP and the OF and show you graphically which OFs are most likely to produce a higher specific impulse. For example, take a look at the following graph, which was computed by the RED for the P-5. Here we can see that around an OF of 8.4, we obtain a maximum theoretical ISP value of 154.3 seconds. If you're familiar with propulsion, you may have already noticed two things. First, the ISP is comparatively low, which is true. This was chosen this way because the P-5 is an experimental low-power engine whose focus is understanding the implications of building a simple thruster with commercially available components. In fact, this project involved a market study with more than 300 quotes analyzed, a financial study of all the systems, and the design of 3 injectors. All of this was done to characterize the economics, manufacturing, logistics, technicalities, and limitations of the project such that all the information could be used to study the feasibility of developing future, more powerful, and holistically efficient engines. Second thing you may have noticed, the mixing ratio is very high, which is also true. This is due to the low purity of the oxidizer, which was a constraint resulting from the scope of the project. We will discuss this when we answer the third question. There were 8 successful hot fires, and now we're going to take a look at some of the data. The tests were numbered arbitrarily. For all these 3-second long hot fires, we can see that the propellant's flow take a while to eventually reach equilibrium at t equals 6 seconds, and thus the mixing ratio takes some time to stabilize too. By taking the average of the stabilized part of the mixing ratio graphs, we can finally solve the first question. Based on the analyzed data, the ignitable mixing ratio range for the August hot fires for the P-5 engine was between 0.51 and 1.37. We know that the maximum ISP occurs at an OF of 8.4, and so we could say that it was only possible to operate the engine at about 16% of its design capacity. Was this because it is not physically possible to burn higher OFs? No, we don't believe so, since in the injector hot fires, we achieved ratios up to 5.2 successfully, which proves that the injector worked well, and that the propellant combination was ignitable. Due to timing, it was not possible to test OFs higher than 5.2, so it's not known if reaching 8.4 ratios would be possible. In these full engine hot fires, all the attempts that failed had mixing ratios above the range we just discovered, but why wouldn't they burn if they did burn in the injector tests? Time to answer question 2. Let's look at hot fires with equivalent mixing ratios, but one with the combustion chamber and the other without it. First, with the combustion chamber. Now only the injector. Before proving that adding the combustion chamber makes the mixture not ignitable with the IFSL method, we're going to further confirm that the low concentrated oxidizer is capable of combusting with the fuel. Going back to theory again, the choice of a liquid oxidizer is very critical. Most of the liquid oxidizers at room temperature are either hypergolic or cryogenic, which leaves the amateur rocket scientist with only 3 options. First, hydrogen peroxide, which has been extensively used in the aerospace industry, and surprisingly it can be purchased in Costa Rica to a weight-to-weight concentration of about 50%. Second, nitrous oxide, which is usually a liquid when stored in commercially available tanks, but needs to be kept at high pressures to remain liquid. And third, nitrous oxide and decomposition byproducts such as nitric oxide, dinitrogen tetraoxide, and nitrogen dioxide. These are very energetic liquid oxidizers, but they cannot be easily purchased since they are extremely dangerous. Therefore, based on the scope of this project, hydrogen peroxide was the best option. The part that worried us the most was not knowing if it would be able to combust with half of its content being water. If the peroxide in fact didn't support combustion, then the options would be to either further concentrate it or switch to a different oxidizer. Even though we already knew that the power of the engine would be badly affected by the low concentration of the peroxide compared to the most common 90% peroxide used in high-power rocketry, we felt that this was the best way to go, since the P-5 needed to be a simple first step. This meant that before even starting to design the engine, we would have to make sure that the peroxide could burn. Therefore, we got some of that 50% solution and experimented with it. In these videos, 50% hydrogen peroxide was added to 96% ethanol in a crucible. There's a lot that can be inferred about what's going on. Here we can see that whenever the crucible is stirred, the fire rises more violently due to the local mixing of the propellants. To understand this, let's look at the diagram to the right. Since the peroxide solution is denser than the ethanol, it sinks at the bottom just like vinegar in olive oil would do. These two layers are separated and they don't mix, since they are not really soluble into each other. The top layer is lit up and it burns independently of the bottom layer due to the presence of oxygen in the atmosphere. Once the crucible is stirred, the peroxide layer sways and overlaps with the ethanol at the top, forming a momentary zone of mixed propellants at the edge. Since there's enough heat from the ethanol that was already burning, all the ingredients from the fire triangle are satisfied, and we see those flame colors that evidence the presence of hydrogen peroxide in a combustion reaction. This phenomenon affirms why it is that we require the injection of the propellants. I always wondered why you could not just mix the propellants together in a tank, shake it, and then send it directly to the engine. And this video proves why not. The propellants must be very well mixed. Of course, you cannot achieve the same levels of mixing by stirring a crucible than by using an actual injector, but this was enough of a proof to affirm that a solution of hydrogen peroxide with 50% water content on it would still burn. As we know, this was further confirmed when we used the injector and reached mixing ratios up to 5.2. Now, let's talk about the physical meaning of the mixing ratio, since the concept we have introduced so far was a simplification of what it really means. We define mathematically the mixing ratio as the ratio between the mass flow rates of the propellants. Suppose that for all the hypothetical injectors shown below, the oxidizer and fuel mass flow rates are the same, and thus they have the same mixing ratio, which equals 1. Do you think all of them will produce the same level of mixing? The answer is no. Of course, they are going to have different mixing efficiencies, and an injector that shoots the propellants away from each other like number 1 wouldn't work at all. Besides the type of injector, there is a more fundamental fact that we must acknowledge, which is that the mixing ratio is not evenly distributed along the spray pattern. There are going to be areas in the propellant cloud that are going to have a higher OF than others. Think about it. Here it's useful to introduce the concept of gradient. If we could assign colors to every single point in the propellant cloud and the color represented the mixing ratio, we would be able to observe the atomization locally and see how the mixing ratio is distributed at a certain time, similar to the image in the left. If we denote the three-dimensional coordinates by x, y, z and use t for time, we could say there is a function r that tells us the mixing ratio at a point x, y, z at a given time t. By taking the gradient, which is essentially the multivariable generalization of the derivative in vector calculus, of this function r, we would be able to see how the mixing ratio changes at different times. For example, in this picture of the injector, the intensity of the orange color of the circles indicates the local mixing ratio. This injector is called a like doublets injector, which means that fuel is impinged against fuel and oxidizer is impinged against oxidizer. The point where this occurs is called primary mixing, which results in fans that then intersect with other adjacent fans. This is known as secondary mixing. Due to the orientation of the orifices in the injector, the resulting spray pattern is mainly an axial cylinder, and its highest OF zone is expected to be close to the y-axis. To even make more realistic our mixing ratio function, we should add two more variables. One for the theoretical mixing ratio representing the mass flow rate, let's call it R sub theo, and another for the ratio of the injection pressures. What I want to say with this is that for different mass flow rates and pressures, it is possible to get different max OF zone locations and distributions. Look at the following pictures from the injector hot fires, and see if you can tell how the distribution varies from test to test due to the different input parameters. The images were ordered from left to right, top to bottom, in order of increasing theoretical mixing ratio, and arrows were added to indicate the distance between the face of the injector and the region of the propellant cloud where combustion begins. This is denoted by Y sub c. As we can see, this distance varies, but in some cases it is small enough such that it is still inside the combustion chamber. It is also interesting to note how the color of the flame changes as the theoretical mixing ratio is increased. So, in summary, when we try to achieve a specific theoretical mixing ratio, the resulting atomization is going to behave like a gradient, producing areas of low and high local mixing ratios, which means some part of the propellant clouds are more flammable than others. Now we're going to try to understand how the geometry of the chamber further affects the ignition method. To do this, we must update our local mixing ratio gradient graph by including the combustion chamber. Let's see some videos of this and see if we can come up with an idea. First, let's remember what the injection looks like without the chamber.
Yes.
Now let's add a plastic container to resemble an engine without diverging nozzle. Now let's use the prototype chamber in a low mass flow rate. Now let's use the actual engine with propellants at a high mass flow rate. We know that the spraying pattern of the injector produces a type of atomized cylinder, but due to the length of the chamber and through diameter, it changes shape to a more liquid rather than vaporized mixture that exits the nozzle in streams. Let's look to the diagram on the right side. First, the propellants are injected in a like-to-like manner and primary mixing occurs. As a result, secondary mixing occurs effectively at a distance y sub c from the injector phase, forming a propellant cloud that is highly flammable due to the high level of atomization. We said this cloud forms a cylinder-like pattern, and so let's call the diameter of the cylinder d sub c, and use some red lines to represent the cylinder. It is clear from the previous images that this diameter is smaller than the chamber's diameter, denoted by d sub capital C. As this cylinder expands downward, ready to combust, it finds an obstruction, since the diameter of the throat, denoted by d sub T, is smaller than its own diameter. When this happens, the droplets that were once atomized start to gather over the converging part of the chamber, forming what we call a recombination zone. The local mixing ratio at the zone is most likely very low, since the propellants become more like liquids again, and we know they are just like oil and vinegar. They don't go together. Afterwards, the accumulated propellants flow out of the engine in a conical stream pattern at a nearly inexistent mixing ratio, just like with the crucible we showed some videos ago. So what can we conclude from this? That the only region that will combust is located at a distance y sub c from the injector face, and we need enough heat at that specific point to start the reaction. Being a little bit more specific, in aerospace engineering, this y sub c we define has to do with a parameter called the characteristic chamber length, denoted L star, which correlates the length of the chamber with the time the propellant stays there. Now, you may have thought, well, why don't make the diameter of the throat big enough so that the propellant cloud can pass through it? Well, the simple answer is that the dimensions of the engine and injector are constrained by a complex set of design equations, and for the P-5, this was not possible, especially because of the tiny injector orifices. The good news is that we don't have to let the propellant cloud to exit the engine untouched for ignition to occur. We have already found a region that's ready to combust. It's just a matter of making the heat reach it. The question is, how do we reach this zone? Well, none of our three ignition methods were able to do that directly, but now we have conceived more methods that focus on getting enough heat to the flammable zone that we will be using in future engines. Let's see what happened with the only successful method we tried. First, we must acknowledge that due to the presence of oxygen in the surrounding air, our propellant is a mixture mainly consisting of liquid ethanol, liquid hydrogen peroxide, liquid water, and gaseous oxygen. Nevertheless, this mixture prevails only outside the combustion chamber. Therefore, we could imagine two different mixtures with two different properties each. Let's call them the external and internal mixture. Based on the conclusion we made recently, we know that the internal mixture will not ignite after the recombination zone. We have seen the videos where adding sources of heat at the throat or exit fails to start the engine. The external mixture nonetheless can be ignited almost anywhere as long as the oxygen to peroxide to ethanol ratio allows it. This means that under certain specific circumstances, the external mixture, which we consider to be not flammable, can be ignited. The required condition is that the external mixture must be fuel-rich enough to combust with the gaseous oxygen available. As a result, heat is produced, and if it's close enough to the internal mixture, it may ignite it, thus starting the engine. You can think of this as a two-step ignition process, where igniting the external mixture with the help of local oxygen helps then igniting the internal one. This is exactly what happened with our successful IFSL hot fires. The amount of fuel injected was high enough that after recombination, the resulting external mixture could still be ignited with the surrounding oxygen. Okay. So how much more fuel than oxidizer are we talking about? Well, we answered that in the last analysis question, and the answer is mixing ratios between 0.51 and 1.37 will burn. Experimentally speaking, theoretical mixing ratios higher than 1.37 will produce an external mixture not fuel-rich enough to light up the internal mixture. What does this mean in terms of the performance of the engine? Well, we will explore this in the next and final analysis question. Before wrapping up this section, there's one more comment I want to do. You may have thought that perhaps it is possible to run the engine by only injecting ethanol, and that really the peroxide had no effect in the combustion reaction. To explain why we believe this is not true, think about the requirement of ethanol to burn without peroxide. We already know the ethanol requires the oxygen from the surrounding air, and since the volume inside the chamber is almost identical to that of a soda can, the initial air inside of it would not be enough to support combustion inside of it for 3 seconds. This is like when you cover a candle with a cup. The oxygen is rapidly consumed and the fire dies out. Another idea you may have had for the successful tests is that perhaps the external mixture did ignite but failed in igniting the internal mixture, therefore the engine did not work. The only way to prove that there was in fact a combustion reaction inside the chamber, and we were not just seeing an external mixture burning with air, is that thrust and chamber pressure were measured. something that requires an internal mixture combustion in order to happen. And as we stated already, the internal mixture cannot burn steadily with the initial oxygen inside the combustion chamber. If you want to take it one step further and say, well, maybe the thrust rating was due to the recoil of the injector, just like when you turn on a water hose and you feel a force pushing you backwards, I would say good thought, but we're sure this wasn't the case. The engine was mounted tight hanging from a support plate, and when a net thrust greater than the engine's own weight, approximately 44 newtons, that is about 4.5 kilograms, is produced, the engine is lifted up by 4 millimeters and exerts pressure into some sensors. This pressure is then translated into a thrust reading. What we mean by this is that the recoil effect should have been stronger than the entire engine's weight in order for that claim to be true. Moreover, since several cold flows with the injector fixed to the sensors were done before, we did know an approximate value of the force produced by this recoil. It is no greater than 5 newtons. To summarize, when the tanks are set to a specific pressure to achieve a theoretical mixing ratio, the resulting spraying is going to have a mixing ratio gradient, which is a function of many factors including the chamber geometry. The engine can only be started by providing enough heat to a region inside the chamber with a high local mixing ratio. All the methods used cannot provide enough heat to this region. Nevertheless, if the theoretical mixing ratio is fuel-rich enough, an external mixture that can be lighted up with the surrounding oxygen will be produced, and it can be ignited to ignite the internal mixture as well. And so, we answer our second analysis question. Any theoretical mixing ratio outside the determined range will not burn due to the ignition method only being able to light up the fuel-rich external mixtures produced in that range. Now we're going to explore the third question, which is how does this theoretical mixing ratio range limitation affects the engine? We're going to have to learn a few more equations to solve this question. Equation 1 is a simplified version of the thrust equation, where some assumptions were made, and they will not be explained in this video. First, we see that the theoretical thrust can be expressed as a function of the total mass flow rate and the exit velocity of the combustion gases. If you remember, I talked about a quantity called the specific impulse, or ISP for short, which equals the exit velocity divided by the acceleration due to gravity, which is denoted by letter G. Also, using some of the equations presented at the beginning of this video, the total mass flow rate can be expressed as a function of the theoretical mixing ratio in either the oxidizer or the fuel mass flow rate. By plugging in these expressions, we get equation 2. Here we note that the product of a mass flow rate and gravity equals a weight flow rate, which has units of newtons per second or pounds per second. This quantity is denoted by capital W dot. Finally, we can use the ISP versus mixing ratio chart we got from the red to derive a mathematical logarithmic model that predicts the ISP for a given OF. Substituting these equations into equation 2, we get equation 3. Again, don't worry if you're having trouble with the math. The important thing to understand here is that we have derived a theoretical equation that tells us how the thrust varies as we vary the theoretical mixing ratio we set in the system. The model derived for the ISP is not entirely valid for low OFs, and in reality it is also a function of the chamber pressure. But the idea is to have a reference model we could use to understand the relationship between the OFs and the thrust. Now, in every test, the weight flow rates are set differently, so our thrust function should be a function of the fuel weight flow rate too. Nevertheless, for simplicity, we're going to assume a constant fuel flow rate equal to 1 and come up with a function that tells us the theoretical performance of the engine as a fraction of the max plant ideal thrust at a mixing ratio of 8.4. Keep in mind that a weight fuel rate equal to 1 is very high, but it will cancel out if held constant. For the P-5, the actual value of this capital W dot would be approximately 0.26 newtons per second. Let's call our new function the optimal thrust fraction and denote it by the acronym OTF. The function was plotted in the graph below. Here we can see that the function is nearly linear, and since our ignition method did not let us exceed a mixing ratio of 1.37, we could say the engine only operated to 20% of its capability. Of course, the thrust produced is not the only way to measure how well the engine did. There are other important parameters that can be measured, such as chamber pressure, efficiencies, and ISP. Next, we will show some of the graphs obtained from the successful hot fire data, disclose some details we think the public should be aware of, and afterwards, we will proceed to the final section of this video, which is the conclusion. Each test lasts 10 seconds, with injection occurring at t equals 4 seconds, a quasi-stabilization of the combustion occurring at about t equals 5 seconds, and turn off of the engine at t equals 7 seconds. The graphs for thrust were taken from the sensor measurements and then fixed to compensate for the weight of the engine. The ISP was calculated based on pressure measurements and flow rate measurements from sensors. If you want to learn more about the engine sensors or fit system, you can click here or in the link below. Now, regarding the chamber pressure readings, we were able to get a faulty measurement from only one test, which is the one in the graph below. We say it is faulty because if you work the equations out, you're going to find out that the chamber pressure read is too low. Nevertheless, the fact that the sensor responded specifically during that time in a logical way evidences the existence of pressure in the chamber due to a combustion reaction. The reason why the measurements were not accurate and the posterior tests didn't report any chamber pressures is due to the assembly. The original plan was to use an 80 cm long bent, 1/8 of an inch internal diameter steel tube welded to the engine such that the combustion gases would travel from the engine to the sensors. Nevertheless, after failing to ignite the engine the first week of August, there was only 1 week left to solve even more challenging problems like ignition itself. And by the time we started looking for something as specific as these steel tube assemblies, there was simply no time to get it, since it had to be custom made. There were then 2 options, either seal the 1mm sensor ports at the engine or improvise the tube assembly. We were able to get the assembly done with several small copper pieces, but we were aware that it would probably fail to take the combustion gases successfully to the sensors. The reason why was because the copper pieces were kept together by fittings that were sealed with high-temperature Teflon tape, and since there were many joints, it was likely that some of the combustion gases would leak out or even gradually damage the Teflon. We believe there was in fact some leakage, since we did get a chamber pressure reading as shown in the graph to the left, but it was way lower than expected. We also believe that Teflon got damaged by the end of the second hot fire date, and the leakage was significantly increased. Nevertheless, to have an idea of what the actual chamber pressure could have been, a thermochemical parameter called the S-specific heat ratio, usually denoted by either a letter K or gamma, can be used to numerically solve for a pressure estimate. To know an approximate value of gamma, the measured parameters from the data were input into NASA's CEA for the mixing ratios used. By doing this, you can change the graph from the left, which stays constant at an atmospheric pressure, to a graph like the one in the right, where we theorize a chamber pressure rating. Of course, this last graph is not to be taken as experimental data by any means. By taking the average values of the stabilized sections of the charts, we can get the maximum thrust, ISP, and chamber pressures obtained. Note that these values in the first row are maximum values and do not necessarily come from the same test. The second row is what we can almost affirm to be able to achieve if we could fix our ignition method. The third row is what we could have technically gotten by fixing our ignition method if we could affirm that OFs higher than 5.2 have ignitable internal mixtures. Here we also present a spec sheet that was made about 1 year ago before testing the engine. It shows what the original design parameters for the engine were, and it is interesting to notice that if we could have ignited an 8.4 OF mixture, we would not have been that far from our original calculations. We will discuss this further in the conclusions section. Now we can answer our third question. The ignitable mixing ratio affects the engine's performance based on thrust capability by limiting it to 20%. Other parameters such as ISP are also affected negatively. In this video, we learned many things about low power propulsion and how complicated it can be to ignite a liquid rocket engine. One of the main objectives of this project was to learn about all the aspects involved in making a liquid rocket engine, and without any doubt, this objective was met. The project went beyond the engineering part and it studied several areas such as the financing and the logistics involved in projects like this. A lot of lessons were learned. There were many things we did wrong, such as our ignition method, our cameras, some of our sensors, and some other decisions, but now we understand better what needs to be improved, repeated, and avoided. Perhaps one of the situations we are currently evaluating is whether calling the P-5 engine project concluded or going for a second round of hot fires. Based on all we explained in this video, there are reasons to believe we could find the right ignition method and go for the 100% capacity, but there is still much information that needs to be analyzed before making a decision. Moreover, taking on this task would require another significant amount of time and resources. The other question you may have is simply, what's next for AREX? Are you building another engine? The answer is yes. The next logical step is another engine member of the P family, but we're not sure when this will happen. It might after retesting the P5 or sometime later this decade. The question we're trying to answer once all our internal documentation of the P5 is completed and evaluated is if it would be better to use the knowledge gained from the P5 to build a next, more powerful, better understood engine, or is it worth it to revisit the P5? We don't know yet. But if you ask me the question, if you could go back to when you started the engine, what would you do differently? I would say many things. I would like to finish this video with a picture that was taken just after the last hot fire we did, and a couple of hours before I had to leave Costa Rica temporarily. From left to right, these were my assistants that day. They were my dad and my grandfather, also named Roy. I was genuinely happy that day, even though I knew that at a technical level, the engine was basically no more than a flamethrower. I knew this was just the beginning, similar to the Wright brothers' first short fly. I was happy not because the engine worked, but because of what I had learned.